Welcome to Power Electronics Education Electronic Book, Lecture 4, Control Rectifiers. This lecture is presented by Dr. FIRUZ ZARE. Now we change the firing angle into 45 degrees. That means in this case the output voltage can be negative, while in a resistive load the output voltage couldn't, because the output current should be negative and then we could turn off the thyristor. But in this case, because I'm inductive load and because the output current is continuous, so that's why when we turn on this thyristor, the current through the thyristor is load current, and because load current is continuous, so that's why we keep this thyristor in an on state. And even this time, over this short period, because the output voltage is getting negative and because the current through the thyristor is positive, so still this one is on. But when we apply gate signal to the second thyristor, so because phase B is greater than phase A, so once we turn on this thyristor, the voltage across this thyristor will be negative. So that's why we turn off this thyristor. So when we change the firing angle into 75 degrees, then here we can see that even over this period, because the output voltage is negative, that doesn't mean that this thyristor should be turned off. The reason is that still the current is positive. That means load current is continuous, positive. That means current through the thyristor is positive, so this one is on. So when we can turn off this thyristor, the time that we apply another gate signal to second thyristor, that means phase B is greater than phase A over this period. And here you can see that phase B is greater than phase C and phase A. So that's why when we apply gate signal into this thyristor, the voltage across the first thyristor becomes negative. So we turn off this thyristor, and then over this time the output voltage equals to phase B. So similar happens to phase C over this period or this period. Now we can analyze the three-phase full-wave rectifier with a resistive load. So in this case we can split these thyristors into the upper set, consists of T1, T3 and T5, and the lower set consists of T2, T4 and T6. So basically we have a half-wave rectifier consists of these thyristors, and half-wave rectifier consists of these thyristors. So we can find this voltage positive terminal and this voltage negative terminal, and then we can find the output voltage. So we can concentrate on this period. So in this case, suppose if you look at the output voltage, suppose phase C is greater than other phases already conduct, and phase B is lower than other phases. So phase B conduct, that means in the upper set, which thyristor can be turned on? This one, because phase C, which is basically here, is greater than other phases. So we have phase C here, and in the lower thyristors, so phase B is lower than other phases, so that's why this thyristor is turned on. So the voltage at this point is VB. Let's concentrate on this interval. So basically at this time we decide to turn on this thyristor because in the upper group, phase A is getting positive and greater than phase B and phase C. So when we apply gate signal into this thyristor, we can turn on this thyristor and we can provide phase A into this terminal, and over this time still phase B appears at this point. So here we can see that phase A over this time minus phase B over this time creates output voltage, which is basically this voltage. So if we look at this voltage, this is VAB. So we have this portion of VAB across the load, and the reason is that this terminal is connected to phase A and this terminal is connected to phase B. So now let's concentrate on next interval. So basically we have VA over this interval connected to this terminal, and now we change the output voltage at this terminal, because before we had phase B connected to negative point. Now we decide to turn on phase C because phase C is lower compared to phase B and phase A. So if we turn on this thyristor in the lower group, then phase C appears at this point. So in this case the output voltage is VAC. So that means line voltage appears across the load. So over this period what we have VAC. In the previous case we had VAB. So in this case, as I described, we can actually look at the first half wave control and the second half wave control. The first one, the top one, create positive voltage and the lower one create negative voltage. So the output voltage is this terminal minus this terminal. So what we can do, we can find the output voltage regarding this section of the output voltage for the positive terminal and this section of voltage for negative terminal, and then finally we can find the output voltage across the load. So over this interval, again we apply gate signal to this thyristor, we turn it on. So beyond this time we have phase B connected to positive terminal and still phase C conducts. That means basically we have phase C over this time, over this period, connected to negative terminal. So here we have phase B, here we have phase C. So the output voltage in this case is line voltage, which is VBC, which appears here, VBC. And this is the current loop. That means we turn on this thyristor, so the current passes through this thyristor and back to this thyristor and then back to the phase C. So in the next interval, basically we turn on this thyristor in the lower group. That means beyond this time phase A appears at this point while still we have phase B on positive terminal. So in this case we have line voltage VBA across the load, which is basically this voltage, which is VBA. So here we can see that the current loop is basically through T3, through the load, back to the T2, back to the phase A, and then back to the phase B. And we can find the load current as well, because we have a resistive load. Here we can see that current waveform is similar to voltage waveform, and the reason is that we have resistive load and the current is basically voltage divided by resistor. So over the last interval, basically in the top group, we apply gauge signal to this thyristor. That means phase C is greater than phase B and A. So in this case, we have phase C in this terminal, and still phase A conducts. We have phase A in this terminal. That means we have line voltage, which is VCA. This is VCA. So in this case we have VCA across the load. So the point is that if we actually look at the top thyristors and bottom thyristors in the top group and the bottom group, so each thyristor conduct for T over 3, and then because we subtract this terminal, this voltage from this voltage, so that's why we have basically line voltage across the load. So if you look at phase A, for example, phase A conducts for 2 over 3, same as phase B, same as phase C. So we have positive voltage generated by this group of thyristors, and then we apply basically gauge signal to the either this thyristor T4 or T6. That means we have this voltage generated by the bottom group of thyristors, and then this terminal equals to this voltage, and this terminal equals to this voltage. So what's the output voltage? Output voltage is this terminal minus this terminal, which is basically line voltage. So at any time, output voltage is this voltage minus this voltage, which is basically line voltage. In order to find the output voltage in a simple way, we can actually change the time axis. So basically, because input voltage, line voltage, appears across the load, so if phase voltage is Vm, if phase voltage is Vm sinus 2 pi T over T, so that means the peak value is Vm. So in line we have, so line voltage max value is root of 3 Vm. So that's why this peak value is root of 3 Vm. And because line voltage appears across the load, so this voltage is line voltage. So to be able to simplify the calculation to find the average voltage, so we can basically simplify this equation and define this voltage in terms of cosine. That means if I move the time axis on this point, suppose this is 0, then we can define this equation as a cosine 2 pi t over t, and the peak is root of 3 Vm. So suppose that the firing time, firing angle, so suppose the firing time is delta t, because each interval in a 3-phase full wave rectifier is t over 6. So half of this one is placed here, which is t over 12, and the half of that one is placed here, minus t over 12. And because the firing time, this interval is defined as delta t, so the lower limit of integral here is minus t over 12 plus delta t, and the upper limit is defined as t over 12 plus delta t. So that's why we can basically find this integral which defines this area as the average voltage over that cycle, and the cycle is t over 6, which is defined here, and the upper limit and the lower limit of the integral. We can simplify this equation. That means integral of cosine at, if this term is a, is sinus at times of 1 over a, which is basically this one is 1 over a, whereas this term is a again. The upper limits of the integral, lower limits of the integral. And when we multiply this term into this term, we have 6 times of root of 3 Vm over t. Then we can simplify again. 6 over 2 is 3, root of 3 Vm over pi. This is a constant value. And then we can multiply again this term. We can put here, which is the upper limit, and we can put here again, which is lower limit. Now we can simplify this equation, because basically this sign is sinus 2 pi t times of t over 12 plus delta t, and this one is sinus. We can simplify this one and simplify this one, which is pi over 6, and then multiply this term into the next term is 2 pi delta t over t. So here you can see that we have this term, similar for the next sign. Again, we can simplify into this equation. That means if this term is a and this term is b, so basically sinus a minus sinus b equals to 2 sinus a minus b over 2 times of cosinus a plus b over 2. So when we subtract a from b divided by 2, that means we have sinus pi over 6. So basically this one means this term, and when we add a and b, we get this term. So we can simplify again, because sine pi over 6 is 1 over 2, which is basically this term. So 2 times of 1 over 2 is 1. So 1 times of cosine 2 pi delta t over t is this term. And we have this term here again. So finally, the output voltage is 3 root of 3 Vm over pi times of cosine alpha, and the reason is that we can find delta t in terms of alpha because one cycle equals to 2 pi in radian. So here we can find that delta t is alpha t over 2 pi, and if we put in this equation we can get cosine alpha. So here by changing alpha we can change the output voltage.